Hi guys! This video contains demonstrations and discussions of the practice exercises found in our modules. Specifically, this video will talk about the practice exercise A on lesson number 3 of our unit number 2. Lesson number 3 is concerned on basic exponential equations. When I say basic, there are some exponential equations that might not be covered in this video in our module and may be covered in the next level or in higher mathematics classes. So we are going to talk about how do we solve exponential equations, because basically when we talk about equations, we are going to solve for a value of the variable that will make the equation true and correct. So sharing to you right now is the screen of the Kotobee reader. Yeah. Okay. At the bottom, I already included the material, so it's already here. So let me open it for you. And this is just the introduction of exponential fractions. As I said, there might be, and I mean exponential equations. There might be some exponential equations that will not be covered here. So we are going to leave that for your higher level mathematics. Or if you would really want to solve for those types of exponential equations, you may ask me for a problem and I could actually give you a sample problem. As of the moment, our concern is with practice exercises already found in your prepared module. We will talk about practice exercises A. So we are going to solve the following exponential equations. When you say solve, we are going to look for the value of the variable, in this case x, which will make the equation true. And of course, when we talk about solving equations, we need to check it as part of our processes. Checking is not actually required, but that is an additional help for us and guidance and will to determine whether answers are correct or not. I have already placed this practice exercise A in another paint application software. So let me share that to you, okay, so that we can actually scribble all of our solutions here. So starting with number 1, we have here for a while. Yeah. We have here 3 to the power of x is equal to 27. Actually, just by looking at the problem, you can just predict what value of x would make the left-hand side equal to the right-hand side value 27. So just by looking at it, if we use 1 for x, 3 to the power of 1, it's not 27. If we use 2, 3 squared, it's not yet 27. But if we use 3, 3 to the cube, the answer is 27. So you could actually use trial and error or guess and test strategy, wherein you can just simply pick test values for x, any value, as long as it will result to the right hand side of the equation, and that means that is the value for x. But there are some instances wherein you cannot just simply take any value, because x here is not necessarily integer, nor it's not necessarily uh, positive integer. We could have negative integers, and definitely the content of unit 2, rational exponents, there are also some instances wherein the value for x may be a fraction. So instead of just by picking any value for guess and test or trial and error strategy, let us use the proper mathematical processes in solving this equation. We are going to use the property of equivalent exponents. The property of equivalent exponents as presented in your module is if we have b to the power of x equals to b to the power of y. If we have same bases, that means that your exponents are also equal. The point here is if we can make the bases similar, we can just simply pick the exponents as equal. So the goal here, number 1, is to create an opportunity for the left-hand side and the right-hand side to become expressions with same basis. So we can just use this one. So 3 is the simplest one of the simplest forms. How do we know, by the way, how do we pick base? Aside from making the two sides of the equations with same bases, you can just simply pick the prime numbers. When you say prime numbers, you pick 2. And then if both cannot be represented by 2, the next prime number is 3. If the both equations cannot be represented by base 3, you pick 5. You could use prime numbers. As to why prime numbers? Because if you will pick, let's say 8, 8 is not a prime number. 8 to the power of something. Take note that 8 can be represented as base 2 as well. If you pick 4, 4 can also be represented as base 2. So there might be plenty of representations for bases. If you're good with that, I'm also good with that. But what I am actually suggesting is for you to use the prime numbers as your basis. Okay, so let us use that for 27. We know that 27 is 3 cubed. We know that 27 is 3 cubed. In this case, we have already same bases. So we have the same base. We can just simply equate the exponent. So we have here x is equal to 3. Okay. So if you're not sure with this answer because you're looking for a solution, simply use the value for x here in our equation. Right? Use the in the equation, substitute it here. So 3 cubed, is it 27? Yes, 27 equals 27. So this is the correct answer. Okay. So again, checking is actually for your own benefit. It's up to you if you would still want to check or not. But I would suggest that you may try checking from time to time. Let's have number 2. Number 2 is 10 to the power of x equals 100,000. Okay. We can express both as base 10. Okay. I mentioned earlier that you could choose prime numbers, but it's easy to use 10 here because we know that this is also a product of base 10 because we only have zeros here. So we can have 10 to the power of x is equal to 10 to the power of how many zeros? 1, 2, 3, 4, 5. 10 to the power of 5. Now we have the same bases, 10, base 10. So we can just simply cut this out, just like what happened earlier. Cut that out. So our solution here is x equals 5. If you would like to check, you can use calculators and take the value or multiply 10 5 times. 10 times 10 times 10 times 10 and times 10 in your calculators. You would know that the answer is 100,000. So this is actually the correct answer. As for number 3, so number 3 is 6 to the power of x equals 1 over 36. When you look at this problem, we cannot just simply say, oh, I can make 1 over 36 as base 6 immediately. Okay. It's already in a fraction form. Okay? So how do we make it as base 6? You can simply pick here the denominator as base 6 because this would become 6 to the power of x equals 1 over 6 squared because 36 is 6 squared. But the two sides are not yet of the same base. What we could do is we could move this up and apply the reverse operation of the law of negative exponents. In the law of negative exponents, if the exponent is a negative number, you can bring it down to make it positive. So reverse, since it's already positive in the denominator, we can bring it up. So this would become 6 to the or x is equal to 6 to the power of negative 2. Negative 2. We brought that up. If we're going to go back there, we can bring it down and make it positive. The point here is we are making the same base. Now, if you have the same base, using the property of equivalent exponents, we can remove this, and therefore our answer is x to the power of negative 2. Checking, let's try it here. 6 to the power of negative 2, it's a negative exponent, you can bring it down. So that's why you have 1 over 6 squared, and then definitely you have 1 over 36. So again, the key here is to make the basis of similar, make this, you create an opportunity for the basis to become similar. Now, if there are instances wherein you cannot really make the base is similar. That is what I meant about we will be leaving it in the higher level mathematics. What we're going to talk about here is the possibility that, that only both sides could become, say, bases. Okay? So this is the first video um, for our practice exercise A on lesson number 3. We will continue with the next video. So hopefully you still stay tuned. That's all. Goodbye.